ถ้าอาจารย์เขาเลื่อนฝากเลื่อนด้วยเนาะ
ได้
วันนี้
ไว้ใจได้ไม่เลื่อนหรอก
ผมตั้งเลย
วันนี้ก็น่าจะเป็นไอ้ที่เขาบอกที่เขาบอกว่า
ผมมีวิธีแล้วเว้ยพี่ทำให้กินกาแฟไงให้มีประสิทธิภาพ
แล้วก็น่าจะเป็นแต่ที่พ่อ
แล้วแต่คนด้วยนะ
กินยังไงกินทั้งจมูก
กูก็กินทั้งขวดแล้ว
เพราะภาษาเป็น
ใช่
So do we have everybody?
เอ้ย
No, not quite. So before Mishael continues with what he started yesterday, I just want to describe very briefly what I sent you, which is essentially about these different nomenclatures that are a little confusing maybe. And want to make one point, and this is that, you know, sometimes we talk about vectors and sometimes we talk about functions. And Mishael is going to show strictly how it's done, but I want to give you one example that relates to what you hopefully know about vectors. I suppose you have learned vectors in high school. Okay. So let's wait 3 minutes until everybody has shown up.
เดี๋ยวเขาไม่ได้สอบไม่รู้เมื่อกี้มาแล้วนี่
Wie ist das fürs Wochenende? Du hast was reserviert.
Ja,
Hast du einen Van auch schon? Oder?
ich habe den Van reserviert, mit immer für mich, an mich, aber sie hat mir
เราไป
nicht
ฉีดแล้วเราก็คิด
zurückgeschrieben.
คำถามได้เลย
Ich mache das immer erst im letzten Moment und jetzt habe ich sie gerade noch einmal gefragt.
Und wann soll der Van fahren?
Um halb vier, glaube ich, nein, Viertel vor vier.
Am Freitag.
Ja, morgen.
Morgen.
จะมีเนี่ยครับ
Ich überlege gerade, du fährst nach Rayon oder nach Pattaya? Oder?
Ja,
Pattaya, gut, dann muss man sehen, ob ich mir irgendein Hotel reservieren kann oder so.
ich kann gerne auch da
จะมีแต่
drüben
ว่าไปดู
reservieren.
กันยังไม่ได้
โพ
ดู
สแมนนี่
Oh ja, dann
มัน
tu
มี
das.
สมการมัน
Ist einfacher.
อ๋อไม่ใช่นะมันแม็กซ์เวลล์นี่หว่าที่เป็นอินฟินิตี้
Ja,
โพ
ja,
สแมนใช่ไหม
เดี๋ยวโบ
Oh, weiß ich, zahle das schon.
ไม่มีใครเชื่อเขา
Muss ja nicht immer
เขา
extra
เชื่อ
was
การที่
zahlen.
เขา
Ich hab ja noch bei mir daheim in einer Ecke, was weiß ich, 10.000 Baht. Und
ja, so ungefähr.
die ich irgendwann mal da abgelegt habe. Die müssen jetzt ausgegeben werden.
ค่าที่เข้ากับคอนตัม
ค่าที่ข้อนี่คืออะไรหรอ
Ja, ja, dann hoffe ich, dass heute Nachmittag die Welt das bestätigt.
ค่าวัตถุที่มีตามวิ่งได้ไม่รู้นะ
พาร์ติเคิล
ใช่ไปเข้าคือมองไปอนุภาคไปเข้าอนุภาค
เป็นก้อนแสงที่บรรจุข้อมูลอินโฟเมชัน
Der Himmel ist blank.
คาซิข้อคืออะไรนะพี่ขอ
ไปเข้าถ้าแปลเป็นไทยก็อนุภาค
คาซิข้อนะ
คาซิ
Ist das alles flackern?
ก็คือแบบทุกอย่างที่อธิบายได้ด้วยกระบวนการบังคับ
Can you try to find which one it is and switch it
แต่
off?
ว่าถ้า
แมคโครมองเป็นแมคโคร
ใช่ที่ใช้ F เท่ากับ V ประมาณนั้นแบบระบบใหญ่
ตอนแรกมันเป็นตรงนี้ใช่ปะ ตอนนี้เป็นตรงนี้แล้ว
เป็นงั้นเนาะ
No.
มันซับสปิริตอินไซ
I mean,
ด์
like it's affected by the in the whole room already. So I don't know why.
Is affected by what?
It's affected the whole room already.
Yeah, but
สตาร์ดี้คอนทับ
No, that's not how it is.
เป็นสิ่งที่เรียนรู้ไว้สักที
ที่คอนติเนีย
switch on all the other ones except that one. Yeah.
แต่ว่าต่อไปมัน
อัน
มา
นี้
เป็น
เอ
เรื่
เจ
อย
ชี
ๆต่อ
ทำอินเดอะมอลล์
คือสอบจบ
Ah, good, like that.
สอบจบ
ค
ผม
น
ก
เมื่
ลั
อ
ว
กี้
การ
เข้ามา
สิ่ง
นั่ง
ด้วย
น่ารักมาก
โอเค
น่ารักที่สุดในมอลล์เนี่ย
อยู่ตำแหน่งนั่นเอง
So let's start.
น่ารักมาก
Let's go.
รู้จักปะ
Please understand
โอ้เหรอ
ออกมาแล้วพี่
ก็น่ารักมากเลยอะ
ไม่เห็นมีเลยอ่ะสวิตช์
Let's go.
So one difficulty with this, with the quantum mechanics, of course, is the concept. I mean, the whole idea of quantum mechanics.
ยืมหน่อย
But one difficulty is also mathematical. And this also comes from the fact that, first of all, it's not easy. I mean, nobody has ever said it's easy. But it also comes from the fact that so many different notations are used. You know, you have this Heisenberg notation and Schrödinger notation. And today, most of the time, we mix the two, so it's quite confusing. So here I've started again with the usual way we write things. And this is, you see, H is Heisenberg, but Schrödinger would write here d2 dx squared plus v, but that's too much to write, so I've used the Heisenberg H. And the rest is Schrödinger's view. Now yesterday, we talked about using this and rearranging a little bit to compute the energy. So what have I done here? I mean, remember that here the order of things is important. So h psi psi is not the same as psi h psi. But what I'm allowed to do, like in any equation, I am allowed to do the same thing on the left-hand side and on the right-hand side. So I take psi and I move psi here and I move psi here and I get this. Right, so people sometimes say I make a sandwich. I mean, you know, I put the psi on one side, the psi on the other side. Now, this here, sometimes you will find written like this, with these brackets. And this is the notation that was invented by Paul Dirac, the one from the Dirac delta function and the one from the spin, so a very famous physicist. And a very big believer in mathematics. I mean, Dirac was, well, you know, he came up with the delta function, so he was really also a very good mathematician. And he made a little joke about this. And he said, well, if this is a bracket, then I will call this a Bra vector and this a Ket vector. Because of bracket, right? This is sometimes mathematically useful to distinguish between Bra and Ket vectors. It is, and do you know about column vectors and row vectors that you use in geometry? Columns and rows? No? Okay, it's pretty much the same thing. We can come back to this very, very soon. So, let's go to this notation, not use Dirac. So I have moved psi 1 here, and where is it written? It's above. I had moved, let's go back so you can see it. I had moved here psi to the left-hand side. Now this is an operator, right? So when there are operators, the order is important. But here there are no operators. E is just a number. E is what we call a scalar. You know, 5 kcal per mole or 3 British thermal units or whatever. It's a number. So if E is a number, I'm allowed to shuffle this side. I mean, I'm allowed to move the elements, and I get this. So I can move the E1 to the front, and I get E1 psi psi. Now, in this writing, you must be careful. Psi psi is not psi square. It's something like psi square, but it's not psi square. Okay? But I can do that fairly easily. And now, and we have not said that, the wave functions usually, okay, so usually have some property that is very useful for us. Namely, what I want to know is E1. Remember the whole thing, the whole purpose was to compute E1. Okay? Now, psi, written like this or written like this, is what I call a scalar product. And I will show you that this is exactly the same as the scalar product that you have learned in high school, hopefully. Okay, maybe we do that at this point. So I say psi is a scalar product. No, I cannot really do it at this point. Okay, I try to do it in such a way that becomes obvious to you. Let's start with the scalar product of two vectors. Two three-dimensional vectors. And you know that is magnitude of A times magnitude of B times cosine of the angle. But there is another way to express this. Do you know how to express this when you know the components of the vector? So now I write my vector A.
Matrix form.
Why is it blue suddenly? As AX, AY, AZ, and leave a little space here. And the same thing with B. Wow. That's the end of it. The blue one was working, or the green one maybe. No. Should sort out the ones that don't work. Okay, doesn't work. A little bit. Bx. Yes, Bx, By, Bz, and maybe some more. So this is vector B, and this is vector A. When the vectors are given like this, how do I compute the scalar product?
The x-axis times the x-axis, right?
Exactly. So the scalar product is a scalar, right? It's a number. Of course, this number is, I write it above, ax times bx plus ay, and this is also dying, ay times by, and it is that. Come on, that cannot be true. ay times by plus az times bz. Okay. This you know from high school. Now comes the trick. Of course, I can write it as sum AI, BI, where I is X or Y, or Z. Okay? And now if I have a four-dimensional vector, so if now my vector it has a fourth component, I don't know what comes after Z. Alpha, let's use the Greek letters now. A alpha, B alpha, A beta, b beta, and we count whichever way we want. Okay, so we have more components. Well, this is very simple to use this expression. Instead of going over x, y, and z, I go over x, y, and z, and all the other ones. So this idea of scalar product, I can very easily generalize from 3 dimensions to an infinite number of dimensions, as big as I want. Okay, now let's look. Maybe we plot the A's. So here I plot AI. And here I have I. So if I equals 1 and AI is something, and I have I equal 2 and AI is something, and I have I equal 3 and AI something, and so forth and so forth and so forth. So this would be 1, 2, 3, 4, 5, 6, 7-dimensional vector. I can do the same for B, of course. So this would be if A is discrete, right? If A is 1 and 2 and 3. And the trick now is I make A continuous. Okay, I make A continuous. This is, I say, well, this is really X. And I define some values everywhere in between. Okay, so now I have many, many, many A's. The A's are defined for any value of X. So A becomes a function of X. Okay? Now I go back to my expression here. This is if A is discrete. So if I have countable A's. If A is continuous, what will become of this expression? How do I have to change this sum if A is not and B, if A and B are not discrete but continuous?
Integrate.
Exactly, I have to integrate. So for continuous variables, this would become integral A of x, B of x, dx over, well, maybe over everything. Because, you know, if there is nothing here and here, then of course the integral is 0, because integral over nothing is nothing. So a sum becomes an integral. A sum is for discrete, and the integral is for continuous. But you see, formally it's exactly the same thing. So this integral here, if I call this a scalar product, I can call this also a scalar product. And sometimes people write like this, sum integral, which means if it is discrete, I use a sum, and if it is continuous, I use an integral, but it's really the same thing. Now we work with computers. Can computers do integrals?
Yes.
Not really. They can approximate integrals. How do they approximate integrals? Have you learned in numerical about the Newton method, trapeze method, or whatever method there are to compute integrals? Well, the computer cannot do integrals. The computer does sum.
Small areas.
Yeah, that's right. The computer divides it into small areas.
Yeah.
So when you do an integral on the computer, you divide it into small areas, and you add up the small area. So on the computer, integrals are sums. because I mean, computers can do multiplications, divisions not so well that you can see, and sums. I mean, that's all a computer can do. And okay, compare. I mean, computer can decide are two numbers the same or not. That's all. So your integral you have to reduce to sums if you want the computer to evaluate it. So this really highlights the fact that sums and integrals are the same. So we have understood now that this integral between two functions can be called a scalar product. And this is exactly what has disappeared here. I don't know what the time constants are when it disappears completely or not completely. Okay. So, we were here, I said this is a scalar product. And so this is what we mean when we write, especially when you write something like this, when you put these brackets, it means sum or integral, depending on whether your psi is continuous or not. Usually it is continuous, it means integral. So psi is really the scalar product of psi with itself. Psi, this is really integral psi of x dx. And I can of course use other functions, so psi phi, that will be integral psi of x phi of x dx. So these things are just shorthand, they're abbreviations. When you see something like that, you know this is an abbreviation. I'm just too lazy to write the integral with all the stuff. Now wave functions, they are usually made in such a way that this integral is 1. The psi integral is 1. And this is called normalization. So wave functions are usually normalized, and that this can be done, you can convince yourself of very easily, because you say if psi is not 1, if psi is c, you just take a new function where you take the old psi and divide by c, and you see that if the old function is an eigenfunction, the new function is also an eigenfunction. Because if you put this into Schrödinger's equation, the c just dropped out on both sides. Okay? So we can normalize our wave functions as we want, and usually they are normalized to 1. So it's very nice. The wave function psi is 1. And so we get what we want and what we discussed yesterday. Psi1 h psi1 is E1 psi1 psi1 is E1 times 1. So this really says if I compute this integral, I get the eigenvalue back, as it should be. I mean, that's what you expect. This is why psi is an eigenfunction. Right? It just gives back the eigenvalue. Okay, but now we can write the thing more fully, so now we will not be so lazy, and we will write the integral. So you see, now I have written the integral, and it's exactly the same thing, but it's just much more complicated, because I have some constant. I've said I'm too lazy to look it up. I don't know what it is. Michelle, maybe you remember. And something h bar or something. And so this is the Hamilton operator, and then here I have just written explicitly the Hamilton operator. So this is the kinetic energy part, this is the potential energy part. the dd2 acts on psi, and this acts also on psi. Oh, and I'm not really very consistent here. I made a mistake. Where is the mistake? Look very carefully and tell me where is the mistake in this equation. You have to look very carefully. I just saw it in big. I didn't see it when it was small. There's a big mistake. One bottle of single beer for who finds the mistake.
Yes, I.
That's right. It says sometimes it says 1 and sometimes it says I. Good point for you. So here it says 1. Of course, it should be I, and here it says I, but here it says 1. I just mistyped. You know, I didn't see the difference between 1 and I. So of course, what I've written here is true for I equal 1, but it's also true for other i's. Okay. So this is just cumbersome, but this is something that you can compute. You know, you can take a function psi, and what is important is you can take any function, not just an eigenfunction. So I can take some other function phi. We call it sometimes trial function because we use it to try out things. Now, what do you know about the integral, about the value of the integral, if instead of using an eigenfunction here and here and here, I use some other function?
Still be like integral would be like 1.
Some normalized. I mean, you're right, the other function should also be normalized. So I take some normalized other function, some normalized trial function. And then what will the value of the integral be? This is nonsense what I've written here. I should not. It's also not equal here. It should be an arrow. there is a character which is called arrow, but it looks very much like the equal sign. So I was too tired when I typed that. I mean, of course, this is not equal here, right? Because this has the Hamiltonian and this has not. So if this is true, then I can do this. So this should be an arrow here. So psi is 1, and then I use maybe some other function phi, and maybe phi is also 1. But what do I know about the value? So I compare the value of the integral. Psi is an eigenfunction. So let's say psi 1 is an eigenfunction. So psi 1 is equal 1. And then I compute psi 1. Let's write the brackets like Mr. Heisenberg or Mr. Dirac. Psi 1 is E1 as we have seen. And now I use some other function, also normalized. Phi, H phi. Equal. So maybe the psi function look like this, and the phi function may be, you know, this could be phi. What do we know about the integral?
At least it's higher than ground.
Exactly, it will be bigger. This is the variational theorem. Any integral that I compute here with some other function except an eigenfunction will give higher value. And so this is what you do when you optimize and search minima and whatever. Keep on computing this and improve. So first thing, you improve the psi by making trial function and see this one better, and so forth.
So just like change the trial function.
That's right.
Iteration.
That's right. This, the main trick is finding the best trial function, and then the best trial function, of course, you say this is the wave function. Decomposed in Gaussians or whatever. Okay. So you should not be afraid of this notation anymore. You see it's just the same thing. And if you know what is a scalar product, like here, you know everything. It's just a generalization. Instead of 3 dimensions, you have either many dimensions or a continuous function, if you believe in functions. But on the computer, of course, we never have continuous functions. Okay, Michel, can you start from here?
Yeah, actually, I wanted to say more or less very similar things to you.
Well, say it again. Enseigner, c'est
Or
répéter.
should
they say
I
in
start
French.
something else? Yeah. No, let me start the same thing, but a little bit. It's a different angle.
French
maybe.
proverb says teaching is iterating. I mean, you have to. And so, and you see, it's the same thing. You can look from one side, and you can look from the other side, and you can look from below, and you can look from above, and you have understood when you see that it's the same thing. You know, you look this way, you look that way, and it's the same thing. Willst du dich hier hinsetzen?
Nein, man kann ja einfach ausstecken. ist
Den
okay.
kannst du einfach ausstecken. Das verträgt er.
Yeah, so this is a little bit what Philip has said actually is a little bit fundamental, but it is a good thing to know because one needs this knowledge in many different places. Let me check. Where do I have my things here? Ah, yes. Here they are. Now, the first thing I want to mention is the idea behind the belief that functions and vectors are actually the same thing. And that goes back to the beginning of the 20th century, and it is actually not so difficult to understand, even so, of course, there's a lot of mathematical proofs and so on. And, that is the thing here. So if mathematically functions and vectors are the same thing, then how does that work? Well, it works in a little bit unusual way. And for example, if you think of a function that is very, very simple, it is only a function that gives function results to the integer values 1 or 2 or 3 or 4 or 5. So it's a function that works not on real numbers but on integer numbers, and also not on every integer number but only on the numbers from 1 to 5. Then this function can be represented as a vector by just writing the result. So you don't need the numbers 1, 2, 3, 4, 5 because they are the index. That's 1, 2, 3, 4, 5. But you don't need to write them. So this vector represents this very, very simple function. And Okay, I want to remove that, yeah. And so the question is now, how does this work with normal functions? Because we are more used to functions over the integer numbers and functions that can have a function value for every input, so for every integer input, not only for some lower limit up to a maximum or upper limit. And the answer is this vector becomes an infinite vector. And the mathematicians, they don't care if a vector is something nice, small like this, or if it's an infinite vector. And so they just say it's exactly like that, but because the real numbers are much more than the integer numbers, the vector becomes infinitely long. And that's how it is done, and that's how functions and vectors are converted into each other. And yeah, so here it is said what I have said. And the second thing that is important is that, also was mentioned by Philip already, a function has a function, if you think sine is a function. But every function that you, where you calculate something numerically, must have a basis. And so if you say a function is sine of x, and x is the set of real numbers, then that's the basis. But this basis can be different. Sometimes you use just the x-axis as a basis. Sometimes you use something like we have learned yesterday, the Gaussian functions as a basis. And why do you do that? You do it because you want to calculate something, and sometimes it's more easy with this basis, and sometimes it's more easy with another basis. And so if you have just the normal numbers, let's say the normal numbers as a function basis, that's what you normally do in mathematics, at least in standard mathematics. This set of, or this basis set is called the Hilbert space. And why is that so? It is so because Mr. Hilbert, which is this guy, he proved that you can express every function as a vector, and then it's more easy very often to work with the vectors. So that's the number one thing that we know now, or we have learned now, just that every function can be treated as a vector. If you want the normal numbers, real numbers, the vector is infinite. Now, of course, if we do a numerical calculation, it is not a good idea to work with infinite numbers. And however, we still use the idea that you can change the basis set in which you work.
Before we go on, maybe you say, by the way, who was Hilbert? Who ever heard about Hilbert? Never heard about Hilbert? Probably the most famous mathematician of the 19th century of all time, I don't know. And the basic thing is Hilbert thought that everything could be demonstrated mathematically. He said maybe we are too stupid, we have not yet found the proof, we have not yet found the demonstration, but eventually we will be able to prove everything. And then came another mathematician who actually proved that not everything can be proved. Who was this other mathematician?
There was even a movie, or maybe a movie on Netflix, I cannot remember, about this other mathematician. It was called The Ghosts of Princeton.
No? Kurt Gödel. G-O, umlaut, G-O-D-E-L. And he really proved that some things cannot be proved.
Something can
That's quite strong.
Yeah.
But this is something that is very important for computer science. Okay? So Hilbert, in some sense, he belongs to the generation of people who thought, like before Max Planck, who thought that nothing more can be discovered. You know, like classical physics, we know everything. We know Maxwell's equation, we know Newton, and that's it. And the equivalent in mathematics is Hilbert. So it's sort of the coronation of classical mathematics. And then came this nasty guy Gödel and said, "Bah, so many things that cannot
There's
be proved."
actually a funny story which is true about Gödel and Hilbert. So Gödel was much younger than Hilbert, and there was once in Germany a radio program where Hilbert was invited to speak about his so-called axiomization of mathematics. And just accidentally, at the same time, there was a small conference where Hilbert's disciples, so his students and co-workers, were giving lectures, and Hilbert could not attend because of this radio broadcasting. And also Kurt Gödel gave his lecture. And after the lecture, at least the more clever of Hilbert's co-workers realized that now Hilbert's program is doomed. And however, nobody dared to tell him. So for maybe 3 years, they did not dare to tell him that in this conference, Gödel
Basically destroyed his program.
So that was that's actually a true story, and Gödel was right.
There's an American author, Douglas Hofstadter. Hofstadter, like the character in the Big Bang Theory, if you know. Do you know the Big Bang Theory?
I know.
Okay. You know, Leonard is called Hofstadter, his family name. And this is because of this Douglas Hofstadter, this author. He wrote a book about Gödel and showed how this is related to music, for instance, of Bach, and how this is related to paintings by Maurits Escher. And the book is called Gödel, Escher, Bach. It won the Pulitzer Prize 30 years ago or something. I mean, I cannot enough recommend this book. It's masterful English. I mean, just the language is beautiful, and it's full of jokes, and you learn in a lot of things, especially about these incompleteness, what they call incompleteness. I wonder it's probably not translated into Thai, so you will have to read it in English.
Yeah, I mean, like if the beauty is in the language already.
You read it very slowly, and sometimes it's very frustrating because it tells you demonstrate this mathematically, so it gives you a little problem. Demonstrate this, and then you sit, I'm so stupid. And then 5 pages later he said, I hope you worked very hard. I can demonstrate that it cannot be demonstrated. So it's a project to read this book. But
It is. It's a little bit old, but it is very.
it's 30 years ago, or something, no, 40 years ago. He got the Pulitzer in the 80s, I think.
now the question is how can one change the basis of a function if one wants to work not in, if one just wants to work in a different basis set, like we have learned that sometimes the Gaussian basis set is very convenient. And actually this is something that you know already probably from high school. And let me go to the other slide. How can I go away from this slide here? Ah, yeah. Okay. No, it doesn't go away. No, it goes away. That is an example of a change of a basis set, because the basis set you can imagine as the coordinate system. The basis set is the same as the coordinate system, because the basis set spans up your function. And so it's really another name, but if you have many basis functions, normally you don't think in terms of coordinate system, but it is like this. And this small picture here just shows the following. The yellow arrow is a function. Well, here it's a vector, but we have learned vectors and functions are the same. And furthermore, it's a very simple vector. It's just a two-dimensional vector. And this is our first set of basis functions, the normal x and y coordinates. And if I change, and in this normal x and y coordinates, the vector has the numerical representation 1 and 0, of course. So 1 is here. And then we change the basis functions, we change the coordinate system to this coordinate system. And then the vector is the same, the function is the same, but as expressed as numbers in this new coordinate system, it's of course different. It has now the coordinate, the component here, and it has the component here, and together they give the same vector. And so the question is how can, and this is the same thing, but another example. Here at the beginning you have this vector in the normal coordinate system with the components 1 and 1, and then if you change it, it's not normalized, but nevertheless it becomes 1 and 0 if you go from this coordinate system to this coordinate system, which is rotated by 45 degrees. And the question is, how can you calculate that? And the answer is, how can you calculate the new numbers if you change the coordinate system? And the answer is, you just have to calculate the matrix that expresses the old coordinate vectors in the new coordinate system. So the matrix that says old x and y are what in the new coordinate system. And in our case, of course, that's a 2 by 2 matrix. Is it written? Here it's written, yeah. In our case, this would be this matrix, because that's the old one expressed in the new one. And so it is very easy. You take the old vector expression, multiply it by the reciprocal of this matrix, and you get then the same vector expressed in the new coordinate system.
Did you learn this in high school, rotating coordinate systems? Yes? So, again, you can do this in 2D, but you can do that in infinites. So your matrix just becomes bigger. Well, that's all.
Now, why did I mention that? I mentioned it because that's just what, or that's just a way how one should think. We have, when we solve our Schrödinger equation, we have the wave function, but the wave function is expressed in terms of the basis functions, which is a coordinate system, and it gives us a set of numbers. Yeah, I have another example actually with Gaussian functions, but I think I will skip over it because it is maybe a little bit time consuming. Now, we know about that we can express our wave function in a basis set, and every basis set is possible, but it must well, of course it's not every basis set is equally good. And now I go to
So the point is, you know, when you have your wave function in one basis set, you can easily get the representation in another basis set. This is like rotating the coordinates. Like you can express your vector in this coordinate system, or you can express it in that coordinate system. And so when you have your wave function, you can express it with basis set A, or basis set B, or basis set B. It's just easy to go from one to the other. Easy, right? Sometimes it takes very big matrices, but
now I go back to our original slide, which of course I will then copy to our Dropbox again. And so here we have the formula. I think it's the same formula that Philip has shown you already, that a function expressed in a basis is normally just written as the sum of the weighted basis functions. So you remember when I was writing yesterday very sloppily, I called these weights C, and here they are called AK, and every wave function is a sum over the basis functions. The basis functions are the phi k, and the x is maybe the coordinates of the electrons, and the weight is this AK, and you can have 30 basis functions for our water molecule, then k goes from 1 to 30.
I mean, to make things clear, I mean, phi here is any function, not just an eigenfunction. You can use any function, well, not any, but any set of function that has some certain properties. In particular, you can use eigenfunctions. So if you have a Hamiltonian and you have the eigenfunction of this Hamiltonian, you can use these eigenfunctions to express some other function. So you can express any function as a linear superposition of eigenfunctions. But very, very generally, it can be any set of functions which have certain properties. They must be orthonormal. That's okay.
Yeah,
So
that's a little bit unfortunate that these things in the mathematical textbooks are called also phi.
I mean, there's not enough letters. I mean, you have to reuse the letters.
And so these phi's, the basis functions, that is fixed. That is something you decide yourself at the beginning of the calculation. And that was the thing that we selected when we said small basis set in our hypercam example, or medium-sized basis set 6, 3, 1, G star. That looked up some basis functions, some Gaussian basis functions. But if you want, you can work with other basis functions. And what you want to calculate are the A's. So the A's are simple numbers. That's the big advantage, especially with the computer. You need to get just the vector of these A's. Each single A is called here AK. And then that what is just called here F, because it's completely general. At the end of the calculation, that is the wave function. And now we know that we can select the basis set, and we are happy with that. And the question is now, however, in the Schrödinger equation, we have this Hamilton operator. And how can we convert this Hamilton operator into a matrix? Well, actually, Philip has mentioned that already. And on the next slide, I think it is just said again. No? Yeah, here. No, sorry, that's not. That's just this condition of autonormality. And maybe if I have here the slide, what does this slide mean? Yeah, it means that you are more happy if the basis functions are orthogonal to each other. That means if two different basis functions multiplied with each other and integrated do not give or give zero.
So we call this a scalar product, right? So Michael says the scalar product between two basis functions, and he has written star, but because sometimes it's complex, so we don't care about the star. So he says the scalar product between two basis functions, or two functions, is 0. How do you call, in our exams disappeared here, how do you call two vectors, A and B, in three-dimensional space, where the scalar product is 0? What do you call two vectors where the scalar product is 0?
Perpendicular vectors.
Yes, perpendicular.
Perpendicular or orthogonal? Orthogonal? Never heard of the word orthogonal?
Something like rectangle, something.
Right, I mean orthogonal means having a right angle. But usually the term orthogonal is used. So we call two vectors orthogonal if their scalar product is 0. And since this integral is a scalar product, we call two functions orthogonal if their scalar product is 0. And we want basis functions to be orthogonal. Oh, that's a little exercise for you to think. Can you? We looked at some wave functions. You know, they look like this or like this. Can you see why? Or it's very easy to see why, for instance, the first and the second eigenfunction of hydrogen atom or of the harmonic oscillator or the particle in the box. Let's take the particle in the box. That's the one where the eigenfunctions look like the string of the guitar. Can you very easily see that they are orthogonal? That the scalar product is 0? Is it very easy to see, or do you really have to do the calculation?
It's conduct. No.
Easy. How?
No, not really easy.
Not really easy? Yeah, very easy.
It's very easy.
It is very easy. Look,
So that would be 1, 2, and 3. Maybe 3.
Michael has already drawn.
Maybe let me draw the
Green.
third one. The third one maybe. Oops.
It doesn't want the third one. Something like this. Okay, now let's just look at the blue and okay, maybe we should draw the 0 line so you see it better if we draw the 0. Well, let's move that one. It's disturbing. So I draw the 0 here, I draw the 0 here. So what I have to do, I have to take each function, maybe the red one at x value and the blue one at x value, and I have to multiply. And then I have to integrate over all this. Can you see that this will be 0?
The red one.
So the red times the blue. Let's multiply, well, the red is not so very nice, but let's multiply the red by the blue. So I will draw here red times blue. Okay, so positive, positive, so it becomes positive.
Yes.
So it looks something like this, but then it becomes 0 because 0 times blue is 0. And then it becomes negative.
Yes.
And then it's finished.
And you see what
And the integral is 0 because this
is a plus.
is exactly the same as this. Okay? So the orthogonality of the wave functions, the fact that the scalar product between two wave functions is 0 is just due to symmetry. I mean, you can try, I mean, if you take the next one that I have removed, if you take the next one and this one, or the next one and this one, it's more complicated, but again, you have same number of positive bumps and negative bumps, and when you integrate, it's 0. Okay? So this is a special property of wave functions. There are, I mean, for those of you who studied linear algebra, this is due to the matrix properties of the Hamilton operator, and Michael is going to tell you how to make a matrix from the Hamilton operator. But this I mean, probably you studied in linear algebra, a symmetric matrix has positive eigenvalue and blah, 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 and an asymmetric matrix has nya, 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 and this is related to this. So our matrices, the Hamilton operator, they make symmetric matrices, as Michael will show.
Now, if you make the calculations with the Gaussian basis functions, for example, with our hypercam program, it actually uses these Gaussian basis functions, and I only mentioned the simplest one, the so-called S-shaped Gaussian basis function, so the one that looked like for example, hydrogen atom square.
Oh, by the way, excuse me for interrupting. Somebody had drawn, was it one of you? When I came, there was a drawing of what we call the Bohr model on the blackboard. Was it some of you who drew this?
Yes.
Yes? You?
No. This guy.
I see. So you probably remember that from high school. And of course the question is, how is this very simplified Bohr model relate to this much better model with the wave functions that we discuss now? It is related, I mean, it's no contradiction. But
It's like each orbit of the Bohr model represents the energy level for each.
in some way, yes. but also the position of where these all circles are drawn. This is also related to the wave function. But I mean, Bohr did not know that because Bohr did not know wave functions. And so Bohr made a guess. I mean, Bohr is really an educated guess. He just said, I think it should be this condition. So he wrote down something and okay, it worked. He got a reasonable answer. And after Schrödinger came and the people said, well, this, you know, the electron is not going like a planet around the sun. So they said, in principle, Bohr's model is wrong because it's sort of a cloud, I mean, it's a density, but still there is some relation. So Bohr's model is not wrong; it is just very rough. I mean, but you actually if you know the wave function, and you can do the mathematics that Bohr did, and then you find these approximative. And I mean, for s orbitals, it is just sort of the maximum of the density. So indeed, the electron is most likely to be found on this S thing, but it does not mean he's there all the time. I mean, it's just a little more likely he's here than he's somewhere else.
Yeah.
I mean, most likely does not mean probability 1.
Yeah, what I wanted to say is something which is again just a little bit important, and that is that we have only spoken about these, let's call it, these basis functions. For example, that one for the hydrogen number 1. Sitting on the hydrogen number 1. And now, if I have the other basis function sitting on the hydrogen number 2, and here would be my oxygen, would these two basis functions integrated, multiplied with each other and integrated, would they give the product 0? I mean, you can just think, if you have here H2 as the coordinate of H2 instead of the coordinate of H1, it would be the basis function number 2 instead of the basis function number 1. This would be BF2.
Would they be orthogonal, or must they be orthogonal, or do you have to make them orthogonal, or what do you think? You see the question?
If you say this is BF1 and this is BF2 and you have to multiply them, well, here it looks like they are far away from each other, so maybe this Gaussian square function is already so low, so small that the product is even smaller and it is very close to 0. But in general, they will not be 0. This integral will not be 0. And therefore, you must make some correction in the real world solving the Schrödinger equation. You must make a correction for the orthonormality. That is just I just say this because you otherwise you might say, aha, but my Gaussian functions they are not they are not, the integration over the product does not become zero. And indeed, it does not become zero. One must either at the beginning mix them so that they become zero when you do this integration over the product, or you solve the Schrödinger equation in a little bit generalized way, then that's also accounted for. Okay, but now the last thing that we don't know. So this thing with the basis functions, that is very general and it has nothing to do with the Schrödinger equation. But now we must go to the Schrödinger equation. And the question is, of course, how we know now that we must find these A's, but where are the A's? A's. Oops, okay, I will come back to the A's. We must find these coefficients A for the basis functions, but how do we do that? And that leads us to the question, how can our Hamilton operator be written as a matrix? So H is an operator, and it should become a matrix. Why should it become a matrix? It should become a matrix because we have our wave function at the end. We want to get it in terms of our basis functions, and so also the Hamilton operator should be written down in terms of the basis functions. And
matrix operations are very frequent, so they're very efficient. I mean, there are many, if you go to what's called numerical library, I mean, a list of routines that are available on your computer to do things, you will find that more than half of the available routines are for matrix. Do this to the matrix, do that to the matrix, compute the eigenvalues, compute the eigenvectors, compute this, compute that. So many problems can be converted into matrix problems. You know, the whole thing with the, you know, scanning, making pictures, all that. So everything is done with some matrix manipulation. So converting taking Mr. Heisenberg seriously and converting everything, not just the function into vectors, but the operators into matrix, this will lead to much more efficient mathematical treatment. So this is what all the programs do.
And fortunately, this is equally simple than setting up a basis set. So we have our basis set. This is the Gaussian basis set with basis function number I. This should be an I. And the Hamilton operator is kinetic plus potential energy.
You see, here there are not the hats on the operators, right? But they are operators. A equal T plus V should be hats. I mean, we are. So here there are no hats, just a different
So it
notation.
should be notified either with bold letters or with a hat or something like that. And I think we mentioned already that the first part, the second derivative, is really an operator because it acts on the thing to the right, but this potential energy is not an operator. It's maybe a complicated thing, but it is just a normal function. And so the recipe is, so you would think maybe the second derivative is more difficult because it's a operator and second derivative and blah blah blah. But actually this is more complicated, this potential energy function, because you have so many electron-electron interactions. And the kinetic energy of the electrons is relatively simple thing. So it's really the same thing as in the particle case, particle in the box and so on. And the recipe is that each element of this Hamilton operator, so maybe I can write it in a blank space here, so the Hamilton operator consists now of elements H1, 1, that pen is a little bit too thick, H1, 2, H1, 3, H1, 4, and here H1N, and so on and so on and so on, and here HNN, and yeah, and so on. And so these are the elements. And each element is given by such an integral like we had it before. Each element, Hij, is equal to the integral of basis function of t applied to, so that's the that's the t applied to basis function I times v of basis function j. The x, but the x is a vector in space. Okay, that's not so. And so these things here are called the matrix elements because they are the elements of the Hamilton matrix. And what is important is after you have calculated this thing, they are just single numbers. What does that mean? Yeah, it's an integration from minus infinity to plus infinity. So you calculate the area under a function. The area under a function is a number. And what is this function? Well, the function is the second derivative of the basis function I. So our Gaussian basis function, one of them, they only differ where they are situated, where is the center of them, and how much is this scaling constant. And the second derivative of a Gaussian function is also a Gaussian function, so that is very handy. That's one of the reasons why one uses Gaussian functions, why one is happy with them. And then the potential energy, okay, that's a formula. Well, for the electronic Schrödinger equation, it's this. All of these Coulomb interactions for the particle in the box it's the formula that says the potential energy is only 0 inside the box and infinite outside the box or whatsoever. So that's just applied to the basis function, and it gives you another function. It gives you it already gives you a number, of course, and the integral. And multiplied both together normally gives you not a Gaussian function because the V destroys this feature of a Gaussian function, but sometimes you even can get a Gaussian function. And important thing, the integral here, the matrix element, is a number. So Hii or Hij equal is called a matrix element. Is a number, some number 0, 0.123, something like that.
So you see the program. I mean, first you select your basis set. Okay? Then you compute all, so you have n, let's say you have n basis functions. From 1 to n. Okay? Then you compute all these little integrals. And you have 100 times 100 little integrals. Basis function 1 with basis function 1, basis function 1, basis function 2. And you put the, so you get 100 times 100 numbers. And these numbers you put in the matrix. Okay? So you have a matrix which is 100 rows, 100 rows, 100 columns, and full of numbers. And then you have the eigenvalue problem like you have learned in somewhere in school or wherever. Big matrix multiplies vector, gives number times the same vector. So this is the matrix eigenvalue problem. Remember the eigenvalue problem of a matrix? This is why we call E the eigenvalue or the eigenenergy. This is why we call psi the eigenvector, because we think of this matrix problem. And computing the eigenvalues and eigenvector of a matrix, this is something very standard in numerical mathematics. So the big duty that you have is computing these 100 times 100 little integrals. It can be done, but it's depending how complicated V is, usually the difficulty is really in the V. It can take some time on your computer.
And now maybe you remember Philip at the beginning of the lecture, because the people don't want to write this thing here all the times, so it is really the notation, the usual Dirac notation is basis function 1 applied to H, and here we would have also basis function 1 at the left upper corner. So that's the Dirac writing, which of course looks much better than if you write always this long line with the formulas.
I mean, of course, you will never have to do it yourself. The program does it automatically. So basically, you can say, well, I don't care, except that sometimes the program makes a mistake. You know, saying I don't care is like when you drive a car and you don't know anything about your car. So if your car stops working, you're completely helpless. You don't know what to do. And then usually you call the garage, and the garage understands he doesn't know anything, and so the bill becomes very long. So what we are seeing, this background, this really becomes important in case of problems. You know, in case your result is not what you expect, or sometimes you get an error message like integral cannot be computed for this or that reason, or the integral is too small, or overflow, or mistakes happen. And then it's good if you have some idea, well, what the heck are these integrals? And what is it trying to do? Why is it doing integrals?
And Well, so if you remember the original Schrödinger equation, H psi equal E psi. Here we have only the Hamilton operator because that's the only thing that we know, that's the input. But in our computer code, we just say we just have a statement like EV, eigenvectors, and EE for eigenenergy equal diagonalize or solve the eigensystem, something like this maybe, of this matrix. And the program is doing it very, very efficiently because it is used to do that for many other things, also besides our special task.
I mean, I don't know what the record is, but I mean, a couple of years ago, people started doing 1 million times 1 million matrix. That's a pretty big, I mean, you know, 1 million times 1 million integrals, I mean, that takes a lot of computing power. And for those of you who are interested in computational aspects, you see that all these integrals are independent of each other. You can compute integral number 2 before or after you compute integral number 1, doesn't make any difference. You just have to put it in the correct place in the matrix. Okay, and this is what you call parallel processing on a computer. So these things are very suitable for parallel processing, right? You tell processor number 1, do the first 1000 integral, then do the second 1000. And so you don't have to wait for the first 1000 to be finished to start with 1001. So this is one advantage. Of course, when you have put them in the matrix, then to diagonalize the matrix, not so easy to make it parallel. But at least, you know, filling the matrix is something you can easily do in parallel.
And then finally the last remark, what is then actually our
It's probably time for a break.
our wave function? Yeah, our wave function are the eigenvectors, the so-called eigenvectors of this matrix, which I called here Eve or EVE. And you get, for example, for the ground state, a vector which is a set of numbers 0, 0. Yeah, I just write a. How was it called? AK. Yeah, so I write A1, A2, A3, A4, and that's our wave function. You have just to multiply it with the basis function, this with the first basis function, this with the second basis function, this with the third one, this with the fourth one, and then you have the nice wave function. And for free, so to say, you get the energies. You get the energies because the Schrödinger equation has a central property, the energy. You could calculate the energy also from the wave function, but the Schrödinger equation gives you the energy right away. That's the EE, the eigenenergy. So that looks very simple, but it is really simple. When you have reached this step, it's easy to solve the Schrödinger equation.
And this is a procedure that is fairly general. I mean, you will see in science other problems where the strategy to do the solution is the same. So here we use this strategy for quantum chemistry or quantum mechanics, but actually this strategy is also used for other problems. Okay, I think we should take a break. Misha, is it time for a break? I think so.
Where's my watch?
You watch the watch. What is the time?
225.
It's 2 to 5.
2 to 5.
Yes.
Okay, so yeah, it's time for a break. So let's take a break, and then I will start looking at these energies. What do we do with these energies? I mean, you know, the wave functions are nice, and you can learn a lot of things. But the first thing usually the chemist looks at is the energy, much more than the wave function. So we discussed already a little bit yesterday what to do with the energies when we talked about whether we can use the harmonic approximation for particle motions. And I will generalize this. So we will generalize this and we will come to something that's called the potential energy surface. Okay, after the break.
Okay.
questions?